Hey guys, it's your host, it's your host Subhra. Welcome to your favorite channel, Subhra the Geek. So today we are on our another video of linear algebra series. This video is on probabilities, schools of thoughts. There are two different schools of thoughts which my great friend Debayan will be talking about. So these are the series which I, along with my very good friend Debayan, have planned for you guys. Debayan has been working as a code data scientist for a company for past couple of years, and he knows all the most of the things which the industry needs, and he will give the insights about what you need and what you need to learn to follow your dream path, the path which will make you get a job in data science, the job which is classified as the sexiest job of the 21st century as per the Harvard Business School. So without further ado, I am your host Shubro, and with me is,
Debayan.
let's start, shall we?
So hi guys, welcome back to this video. Today we're going to talking about something important in a very different sense, in a different very sense in data science. When you talk about statistics, there are two schools of thought when it comes to statisticians and approaching a problem using statistics. One is called the frequentist way of thinking, and the other is a Bayesian way of thinking. You might have heard of these terms previously, and even if you haven't heard of them, you might have used them in some capacity or other in your high school maths or in your college maths or undergrad or somewhere. These sort of come in a way in which they allow you to literally change the way that you approach the problem, change the problem statement, if I may, if you consider these two schools of thought. Without delaying, let's just straight jump into it. To 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 illustrate how it's different, let's start with a very simple anecdote that I have created for you guys to sort of understand and wrap your heads around what it means to have a frequentist way of thinking and what it means to have a Bayesian way of thinking. So consider a scenario, right? So you have misplaced your smartphone somewhere in your home, right? So you can't find it, right? So you're looking for it and you can't find it. So you could use the phone locator, the Android smartphone or the iOS smartphone locator on the base of the instrument, right? So you can locate the phone using a PC or someone else's phone on the browser if you want. So when you use the phone locator and you press on it the app, there's a button and starts ringing, right? Where your phone is, it starts ringing, and you can sort of follow the sound and try to find out, okay, where is it ringing from, right? So my question to you is this: since you know your house and you can hear the sound that's coming from one of the rooms in your house, where do you start searching it for at first, right? So you know it's coming from somewhere and you can hear it, so you know it's in the house. Where do you start searching for that phone? Where do you go to your living room? Do you go to your kitchen? Do you go to your bedroom? Where do you start? If you are a frequentist, like you approach you're in the frequentist way of thinking, you would reason something along these lines. You'd say that I can hear the phone ringing. I also have a mental model, right, of my home, where the rooms are and how they are connected. So you could use that to help you understand which area of the house the sound is coming from. So when you hear the phone ring, right, you could infer, okay, it's coming from that side or it's coming from that side, and you go towards there based on where the sound is coming, where you think the sound is coming from. That's the frequentist way of thinking. If you do not find it there, From that point you will find, we will start thinking, okay, where's the closest point which I think the sound is coming from, and then you will go to that second place. This is the frequentist way of thinking. In a Bayesian way of thinking, you do something clever. You say, okay, I can hear my phone ringing. I have my mental model of my home, where all the rooms are, how they're located, how they're connected, and you could sort of help you understand. Okay, I need to go from here to here to understand where the noise is coming from. That's all there. It's just the same as the frequentist way of thinking. But you also know, or at least aware, where you generally misplace your phone, right? So probably you might have a habit of leaving your phone in the bedroom or nearby your study desk when you come out, right? So if you're at the door and you say, okay, where do I start my search from? You could use that conception, your previous history of you forgetting your phone, and say, okay, I'm going to start my search in my study room and then go to my bedroom. And then if I couldn't find it over there, then I will look for elsewhere based on where I think the sound is coming from. So what you do is that you know the locations where you misplaced the phone in the past. You sort of combine your previous experience with your current way of thinking as sort of like a modified inferencing, right? So you're using your previous history as a way to influence your current way of thinking, your current inference process, and then you can easily or find out where your phone is located. And albeit very, I believe it will be faster than the frequentist way if it's really where you have lost your phone. Like if your assumptions are correct, right? If they're not correct, then you fall back on the frequentist way of thinking. Could you notice the difference between those two way of thinking, right? In the first way, which is the frequentist way, you do not make any assumptions. You just go one place to other and say, okay, each of the rooms have equal probability of having my phone somewhere else, right? And you go to that room and find out whether it's there or not. So you go there, you confirm yes or no. It's a binary decision. You say it's here or it's not here. If you get the phone, that's okay. If you do not get the phone, you move on to the next room. In a Bayesian way of thinking, you start searching the solution for your problem with an assumption about the solution. Where could you possibly find the phone? You say, you look up your history, you look up your previous experience, right? There is some subjectivity you're introducing into the problem statement. You say, based on my experience, I think I must have forgotten my phone either near my, my study desk or in my bedroom. So you start from there. If you do not find it there, then you go by a normal frequentist way. This is the core difference. One, where you have an assumption and you follow the assumption and then make your inference. And in the other, you do not have any prior assumptions. You start off blank. You start off with a blank slate, and then you assign equal probability all outcome, and then go according to that. I'm going to illustrate this concept diagrammatically now. So now we would like to explore in more detail what it means to have a frequentist way of thinking, or what it means to do frequentist statistics. So one of the first things that you do when you open up any probability in statistics is you start with with a concept of a sample space or a universal set. In sample space, you define all the possible outcomes your event or your condition can have, and you list them out one after the other, right? So this is what you would call a universal set. It's all the possible combination that you can think of for that event. When you define a probability, what you do is you take a subset of that and then calculate a ratio, right? So this is the universal set. It contains everything. Let's define an event just to have a very concrete understanding of what it means to define all possible solutions, and then what it means to take a subset of it. Consider an event where you roll two dice, six-sided dice at the same time, right? So let me write it down. Rolling two dices at the same time. So these are six-sided, just to be very explicit about what kind of dice those are. So when you roll them simultaneously, every roll, every 2 times roll is one event. You define that as one event. So when you do it many times, you'd get a set of results. You'd get a pair of numbers that you see on the dice, on the top of the dice. What's the universal set for that event? You do that by taking a permutation of all possible combinations of the 6 numbers. So we can do it like this. We can create a table of the 6 numbers, and then we paid it up. This is like a shortcut way of doing things, right? So if you roll a dice, if you roll 2 dice at the same time, you can get results like this. So 1 1 1 2 1 3, and so on and so forth. Over here you can get 2 1 3 1, and so on and so forth. How many results do you think we are getting? So this whole thing corresponds to 36 possibilities. This is your universal set. This is your sample space, right? So if you say that I want all those, I want probability of events where the numbers, each of those 2 numbers, when you roll when you roll the 2 dice are the same. Let's say that's a desirable event. You want to calculate the probability of happening, right? So what you would do, you would find out from this solution space, from this universal set, which are the ones which satisfy that criteria which you have set, your desirable criteria set, right? So so from these 36 possibilities, you'd see that elements where the numbers are the same, which are 1 1 1 2, sorry, what 2 2 3 3 up till 6 6. So these are the 6 possibilities out of your 36 possibilities which satisfy your desirable criteria, right? So you'd say the probability of you getting an event, right, where both of the dices give you a number which are equal is 6 out of 36, or 1 by 6. So this is your answer, right? This is the frequentist way of thinking. Why? When you define the event, what you did was you had no previous assumption or ideas about what happened and here and there. You just started off with all the solution space, with the entire set at your hand. You know what you can possibly expect, like everything about the event. There is no sense of like, I do not know what can happen or might happen, right? Then from that set, what you do is you take a small subset of it. You say, give me all the numbers where the both of the dice give you the same number. That's a desirable criteria. You're taking a subset of those possibilities. It cannot exceed outside the universal set, right? So when you do that, subsetting, right, you'd see that all the numbers sort of pile up over here along the diagonal, right? So you'd say you select this subset like this. It's still a part of the universal set, right? So you know all the possible solutions, and then you pick the solutions that are favorable to what you defined, and you say it's this is my ratio. This is the ratio of finding my desirable result among all possible outcomes. You know the limits of what can happen. In a Bayesian way of thinking, you have no idea what can happen. You do not know what are the limits of what can happen, right? Or you have incomplete information in some aspect, and you need to make a prior assumption about what can be. Then you see the data, you say, okay, now I will update myself and then work alongside it. Let me explain that a brief more detail. Okay, let's start with Bayesian statistics, the Bayesian way of thinking. This approach, or this school of thought, was pioneered by a French mathematician called Bayes. and what he put forward laid the foundation of, like, in my personal opinion, the whole idea of scientific approach and what it means to have a scientific perspective towards incomplete data, towards things that you do not know, things that you're uncertain of, and how do you combat that uncertainty in everything that you see and work with. I have taken a sort of plot, right? This is a plot made in Python, um, from a Stack Overflow post that sort of very intuitively describes what it means to have a Bayesian way of thinking, right? So what you see over here is a term, like, 16 graphs, right? And each of these graphs depict a piece of information where your your normal distribution, right? These are the bell curve. Your bell curve is sort of like it's sort of like decrease in terms of breadth, like the lengthwise, and sort of converge in on a single point on the x-axis. That's what it sort of starts with a very fat base, and then it slowly gets closer and thinner, and then converges on to a specific number on the x-axis, right? The red line.
Debayan, could you zoom in a bit?
Sure.
Yeah.
So the red line that you can see um, is a true value which the Gaussian should be able to sort of converge at. The Gaussian doesn't know that, so it should converge at that number, right? And on the x-axis, you can see a range of -4 to 6, right? So
So,
the Gaussian,
Debayan, you mentioned the term Gaussian. Could you please tell our audiences what is a Gaussian over here?
the Gaussian is a normal distribution, which is essentially you define the shape as a bell curve, right? A Gaussian looks something along the lines of like this,
Inverted
right?
bell.
Yes, it looks like this, right? And the standard Gaussian or the standard normal distribution has its mean at 0
And median
and the
also.
standard deviation, which is sigma, at 1, right? This is your standard distribution. Obviously, your mean and your standard deviation can change, but essentially the condition is that it should look like a curve, right? And all of them follow certain very interesting properties, which we will be discussing in the next video.
We have discussed in our last video also.
We will improve upon that. We will
Yeah.
improve upon that. We'll provide more contextual understanding. What does it mean to have a mean 0, standard deviation 1? What does it mean to have different values than that?
Yeah.
So if you can look up the previous video to get a what you would call a shallow understanding, but in our next video we'll provide a more in-depth understanding of what it really means to say a Gaussian distribution, right? So coming back to the topic at hand, these are all normal distributions given by the shape. They can be crude, but they're effectively normal, approximately normal, and they seem to be moving about the red line, right? They seem to move in about the red line, and the more and more iterations, n is the iterations, or you're looping sort of. The more and more you sort of iterate, and more you can see that the Gaussian sort of converging and sort of decreasing its variance towards one number on the x-axis, right? So where does Bayesian come into this? In Bayesian, you start with an assumption. Over here, the assumption is that I do not know the mean of a certain set of numbers, right? You have an incomplete set of numbers. You do not have the complete set. Think of a machine learning problem. Think of a financial problem. Think of any data set where you do not have the data. You have some parts of the data, other parts are left out. You'd like to understand what is the mean of this data. What's the mean of the set of numbers? How do you do that? You could not say with certainty about the mean of the problem or the mean of the data set. So what you can do is say, I am some percentage amount of certain that this is the mean of the data set. If you give me more data, I will update myself, I will update my understanding and give you an updated value of what the mean can be with a certainty percentage. That is what it means to be Bayesian. It's changing. You provide me evidence of data, I will update my hypothesis, I will update my ideas, I will update my assumptions, right? So you start off with a blank slate. You do not know anything about the data. You got one data point. You say, okay, so I do not know the mean of that data set. I do not know. It can be any operation. And you can say, I do not know the median of that operation. I do not know some part, some value, some factor of that, some operation on that data set, on the data. What do I start with? You start with an assumption. You say, over here, I say, I do not know the mean of the data set. I have incomplete data. So what do? I say, just start off somewhere, start off somewhere over here, right? That's my, so if you're colorblind, right? Just for you, let me change my color and use something totally different. Let's start with blue, right? So that's my initial assumption. In Bayesian statistics, we call that the prior assumption, or in short, prior. What's my prior for this problem statement, right? You say, okay, my prior is at someone along the lines of 0, right? Obviously, there can be a precise number over here, but I'm saying that I do not know anything. Let's start with 0, right? And what I do have is some understanding of the variance of the data set, right? In Bayesian statistics, you always need to have some part of the problem done, or in a sense that you need to know some part of the problem fixed. Keep that part of the problem fixed. Work on the variable part, and then you do the interchange. You keep this fixed, and then work on the variable part. Over here, I kept my mean variable, or my mean unknown totally, and then I said my standard deviation is this. I have a fixed standard deviation. I know the standard deviation like this. I'm going to update my standard deviation and my mean based on the new data that I get one by one. It's incremental learning. As I get more data, I will update my understanding. I will update my graph, right? You start off with over here for n is equal to 1, right? In the third iteration, you got some outlier data. You got some very large number. Like, so if the mean was really at along the lines of 1.5 or 1.7, you got a number like 10. It's totally out of bounds. It's totally towards the right side, right? So what do? You sort of updates. Okay, so last time I got it around 0. Then you give me a number 10. So you're still uncertain, right? You still do not know what the mean can be. But you say, I'm gonna shift my understanding. I'm gonna say, I think my mean is somewhere over here. If you say that the next number is 10, and I've seen the next previous number was 0, I'm gonna shift my understanding and say, I think my mean is somewhere over here, right? This is my updation. I'm updating my understanding with new data. I got two more data points, and I say, okay, I think given what you have said me, what you have told to me, it's around 2 or 2.5 or something, right? You got two more numbers over there for n equal to 5, and you say next you got something along the lines of like like 4, 3 and 2, right? Let's say you got something along those lines. You say, okay, I got 0, 10, 11, and then you give me 3 and 4. So I'm gonna shift it to the left again, because I'm changing my uncertainty based on the kind of data that I'm getting. So I'm gonna shift it back again a bit, slightly, but a bit, but I'm shift it to the left, right? See, it's almost like dancing, right? It's dancing around the actual answer, which I do not know, right? But since we have marked the answer as in a red line, right? So we are sort of shifting left and right based on new data and slowly decreasing our variance. What does variance mean? Variance means the deviation from the mean, or deviation from the actual answer in this case, right? The more uncertain I am, the more the more uncertain will my results be, will my predictions be. So what I'm going to do, I'm going to deviate a lot. The more and more data that I get, I'm going to deviate less and less. That's the crucial concept. You're decreasing your uncertainty by getting more data, and you're updating your understanding, and you're increasing your confidence about the data, what it means to have. That's what it means to be Bayesian, right? So when you get two more data points, then you again shift over here.
So
You shift to
Debayan, I
left.
think you wrote the sign of variance wrong. That's standard deviation, if I'm not wrong.
Oh, sorry, yeah, that's that's standard deviation.
Yeah,
If you square it,
yeah. Then we get the
sorry,
variance.
yeah, honest mistake, yeah. So it's sigma square. That's variance,
Yeah.
right? So we're trying to decrease the variance as and when we get more data, and it will happen by definition. I'm gonna talk about that definition a bit later. First, let me give you an understanding what it means to be like this. So we get more data points. We are shifting right a bit and left. You see, as and as we get more data, the thickness, the base, right, the variance sigma squared, it's decreasing. Please notice that. So over here, it shifted a left a bit, right a bit. Again, it didn't change over here at all. So it stayed still, right? So it thought you got some data, it was not enough to convince you to shift your opinion, to shift your understanding, to shift your model or your understanding of what the assumption of you have the mean. So you don't change at all. If your evidence is not convincing enough, you do not shift your position, right? That's how the scientific attitude works. So okay, you got some understanding, it's still not good enough, so you don't shift at all. You don't shift. You shift a bit. Can you see the difference? It shifted over here left. It's coming closer. It's coming closer. And then by the last row, you can almost see that it's very near to what the actual mean is, and the variance is very low now. That means it's increasing its confidence a lot. It's saying that I'm pretty sure it's someone around there over here, right? So by the time you reach over here, this variance, right? So the variance over here, let's say this is the last one, and this variance over here, middle, and this is the variance after I got three data points, right? First, let's say first. So you can see the variance of the first one is larger than the variance of the middle one, and this one and the variance of the middle one is larger than the variance of the last one, right? So the more and more data that you get, the better that you get at prediction, the better that you get with your uncertainty, and you can be more confident about what your results is. Don't you think this is drastically different in what you did with frequentist statistics? You already know everything in frequentist statistics. You're just saying, okay, these are the things that I want. What's the ratio? That's frequentist way of thinking. You have the complete information. But in real life, you don't know anything. Most of the times you have half of your data set. Some of your data set is even wrong. What do you do with that data set? How do you make predictions with a confidence level, strong confidence level? Otherwise, no one will work with your models, work with your what you have to say, right? How do you work with that? You approach in a Bayesian way. You say, given the data that I have, given my understanding of the data, what can I say about the data? What can I say about certain statistics about the data? This is where Bayes' law comes into place. That's why it's called the Bayesian way of thinking, because Bayes' law is that step that allows you to do this shift, right? You're thinking, right? How am I shifting? When I say I shifted to the left and right, what does it mean to shift left and right? This is what it means. This is Bayes' law. If you haven't looked at this, then maybe it's your first time. But I'm very confident you must have seen this or heard about this in some aspect or other. So this is the law that's governing this step about shifting left and right towards your actual answer and decrease in your variance. On the left hand side, you have a conditional probability. Please look up our previous videos on what it means to have a conditional probability defined like this: A given B. Like if you want a short short disclaimer of what it means that, let's say there's two events, event A and event B. They have their own individual probabilities of happening, right? So when you say probability of A given B, what you're asking is, given that event B happened, what is the probability then of event A happening? It's a conditional thing. So unless event B happens, you cannot compute the desirable space or the subset, if you're thinking in a frequentist way, of what probability of A can be, right? So that's what it means, A given B. On the right hand side, you can see this denominator, it's A, B given A, right?
It's
so what the formula
numerator,
says,
I guess, Debayan.
sorry, yeah, the numerator, yeah. So what this means is that if you interchange the events or the probability of events happening, you're saying what's the probability of event B happening if A has happened, right? Now, obviously, you can provide your own context about what A and B can be, right? But in generic terms, what it says over here is that you need to know these two terms you will always find something that correlates to this one. You'd always start with some assumptions of what it can be. These are from the data set itself. You need to find out your data set and extract some numbers from probability of BNA, right? And this is where the magic happens, right? Probability of A over here, let's say A is your target event, this is what you want to find out, and B is something that you already know and or you can define by yourself, right? You always need to work with something that you know, and then with something that is variable or something that is uncertain, and you need to quantify that uncertainty and decrease your uncertainty about that specific variable, right? You always work with along in a relative way. So you say probability of A is my prior assumption. When you start off n is equal to 1, you say I have a probability, I call the probability of A. This is always my prior. You multiply this with this fraction, which you should obtain from the data set, from your data, right? And then if you multiply this, you will get an answer, a probability, which is called the posterior probability. The word posterior means afterwards, right? You have a prior assumption, you got more data, you calculate these two numbers, you update your prior assumption, and then you get a posterior assumption. If you are if you were 50% uncertain, so you're not certain at all, it's 50-50, right? You got more data, you got more evidence, and then you say, okay, now I'm 60% certain that this will happen. Earlier you were 50% certain, right? This is how it means. So the more and more data that you will get, right, the more and more this will help you change into the posterior. Now you might ask, okay, now I got n equal to 1, I got my posterior probability after calculating n equal to 1. How do I move to step n equal to 3 and then do my shifting again? How does the loop happen? How does the looping happen in my iterative procedure of finding what the actual answer is, or what can the actual answer be? What you do is plug in back your posterior into the prior, right? So this is an updation statement. If you do machine learning, you must have heard of gradient descent. What you do is update your previous gradient with your current gradient, and then you find the next gradient. This is your updation statement. In Bayesian statistics, this is your this is the same as that gradient descent concept. You update your previous value with your new value, and then work with the new value to update your third new value, right? So when you do n equal to 1, you have nothing, you have no assumptions, nothing. You start with a very basic assumption. Let's say I don't know anything, just start with 50%, n is equal to 0, right? In this case, you use your data, then you say, okay, I think n is equal to around 2.1 or 2.3, right? Then that probability, that posterior probability from n equal to 1 becomes your prior probability for n equal to 3, right? So you have your prior, so the probability of this is your prior, and then this is your posterior, right? This number then becomes your prior for the second step, and then you get a new number. Then you use this again as a prior for this number. Can you see that chain thing, right? You do not know anything, you start with a blank slate, you say I'm not certain about anything, I'm 50% certain about this will happen, random chance. You got more data, you say, okay, 60%. Then you will use that 60% chance because you already know, you have already quantified to yourself that this is a 60% chance given that what I've seen with 1 or 2 data. You get more data, you say, no, okay, 60%, it's 61% given the quality of the data set that I've seen. That step, how much you're jumping, defines on the fraction which you get from the new data that's coming in, right? And you can iterate this infinite times, or as long as you have data or more data coming in, and you do incremental learning. You learn as the data comes in, and it becomes a live process until you reach a state where you're very sure, like the variance is very small. You're confident that, okay, after 100 iterations, I think I've got a correct answer. I don't need to do any more. Then you stop, and then you will have your answer. This is drastically different from what you think frequentist statistics are. Most of our times, you only deal with frequentist statistics because it's the easy way out. It works, and if you know what's happening, if you have domain expertise, you can tell what's happening. You can sort of count it out, and it's a hack. It gives you a correct answer most of the times. But In the case of certain machine learning problems, when you do not know what's happening, you do not have any understanding of the data or what it can be in the future. If the data changes suddenly, it's a time series kind of thing. It can change. It has seasonality. What do? Right? You can't just keep your fixed assumptions like these are what will happen, and then you will stay within that universal set. That's limiting. You're sort of limiting the performance of your model. Why will you do that? You take an open-minded approach. You say, I have an assumption. I can be wrong. Prove me wrong with more data. Your data comes in, you update your hypothesis. You say, okay, now I think this based on what I've seen. More data comes in, then you update that as well. And then you chain that process as and more data comes in. Your model will start learning. It's almost like a learning procedure, right? So this is the magic of Bayesian thinking. And I think more and more of us should really try to understand what it means to have a Bayesian way of thinking.
So, Debayan, that was a great insight on the probability schools of thoughts today. So, thank you and for sharing your insights. So, guys, as I have told you earlier several times, that if you have any problem or you want to suggest anything, please do comment. And we have our exclusive Discord server ready for you guys, where I and Debayan will be helping you guys in each and every step of your journey. So follow that. You can go over there and comment on us, anything. And guys, please, if you like the video, give a like and share it with all your friends who you think will need this kind of information and will help them in their future, near future. And for staying updated, what you need to do is nothing. It's not rocket science. You just need to subscribe the channel and hit the bell notification icon beside it, so that you get notified each and every time we update our channel with a new video on the series or a new series which we are planning. So guys, that's all for the day. I am your host Subhra, and with me is
Debayan.
signing off. Bye bye.